picture of this earlier. It's got a schedule we'll send out in our mind in case you need a digital copy of it. I do recommend starting to study now so that you're not trying to do it all at the last minute. And it helps you get the association together. There is, I will openly tell you, there is a trick, and whenever we go through nomenclature, I'll teach you so that you can name it better, but you don't want me to teach you the trick now, because if I taught you the trick now, then it opens the whole world up of questions and makes life a lot more interesting. So we'll stick with those 25. Those 25 will be plenty. I gave you this big, huge list so that you could see that there is more out there than just the 25 that we'll focus on. But pretty much everything you'll see within this class is within those 25, and really, we don't even focus on those full 25. We'll probably dance around with maybe 15 of them. But continuing on with this Lewis structure, I wanted to do nitrite, so I thought it'd be a good example for you. So rolling through it, the steps are not here, but you should be getting a feel for the steps now. So step 1 is find the center atom. In this case, the center atom will be what? N, or nitrogen. Why is it nitrogen?
Because there's only one of them.
That is not the reason why. It's the lowest electronegative. The one with the lowest electronegativity. From here, we go step 2, draw the skeleton. So we put bonds. And along with that, we get full octets where required. On this oxygen, once a full octet, how many lone pairs do we put on it? 3. 6 electrons. Okay, the reason we do that is, remember, these bonds are counting as 2 electrons. I'm going to be honest with you about this point. I feel like I say the same thing time and time again. So if you're not getting this, you need to come ask me questions. Monday, whenever you guys come in here, we're actually going to have a practice sheet on this, because there's only so many of these I can do and still keep my sanity. Nitrogen, how many lone pairs? 2. For this oxygen, how many lone pairs? 3 again. Alright, so there's step 2. Step 3, we calculate how many electrons we are to represent. Have we used any bit of the periodic table yet? No, notice that. We haven't looked at the periodic table yet. There's no reason to just jump to the periodic table. Alright?
Mr. Clark, wait a minute. Shouldn't you use the periodic table analysis to figure out the electronegativity?
Or you can just use the trim.
I mean, you can, but just in case, Mr.
Sure, if that makes it better for you.
Okay, yeah, it does.
Alright, so from here, calculating the total number of electrons we are to show, we have how many nitrogens? 1. How many oxygens? 2. If you don't know where we got the 1 and the 2 from, there's not a number next to the nitrogen, which means it's like math. When there's not a 1 in front of the X, there's just X. It means there's 1 of them. And we got the 2 there for the oxygen. So from here, how many valence electrons per nitrogen? Why did you get 5?
Because it's in the 15th column.
15th column. You see how this is repetitive? We just keep saying the same thing. How many valence electrons per oxygen?
6, because it's in the 16th column.
Yet again, we're repeating ourselves. Alright, 1 times 5, 5, 2 times 6, 12, add those together, 17, but remember, step 3 is where we take care of the charge. There is a negative, so should we add or subtract? Add, because you're adding negative charges.
So if it's a positive, where
Subtract.
shall I
You got to think what these electrons are.
Why is it
Negative
one?
charge. pass the charge of the poly.
Where'd you get one?
From the negative one up there.
Where's
Because
that?
it's
The
okay.
negative sign.
It's the negative.
Up at the top, like the NO2 negative.
Where the purple circle is.
Yeah, that, because it's important.
All right,
Back
so
strong.
exactly. We have to show 18 electrons.
Yes, sir.
We can only show 18 electrons. That's the max of what we can show. So let's count it up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Snap, crackle, and pop. We got 20.
What a surprise.
Okay, so
Double
we're going to throw a
bond.
double bond. I can't remember what step we're at. Is this 4 now?
Something like that.
Sounds great.
No, we're at 5.
Great.
Either
Left
way,
or right?
it doesn't matter.
Right.
Because you're going to have to draw a resonance structure for it.
Somebody said right. Am I good?
No, erase an electron pair for both nitrogen and oxygen.
Why are we erasing those pairs?
Because we added the bonds here.
Added.
The octet rule.
Because you're breaking the octet rule if you do not remove it off.
Yes.
Realize when I'm asking these questions, I'm looking for the scientific reasons. Scientific, that's a word. Say that to Miss Steffi today. Watch her screen crawl. Yeah. You ever done anything scientific, Miss Steffi? Say what?
Solo.
She probably won't even be able to say it. All right, so count it up. Are we good now? All right, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 of them. We done?
No. Show your charge. Check your signs.
Okay, so what charge? Is there a charge here?
Yes.
How do you know there's a charge?
Because there's a negative.
Because
Because there's a charge there. It was literally
6 minus 7 tells me.
All right, so in this case, we're going to start here. Remember, okay, I'm not doing this now because remember, we're doing this mentally. We're not doing this physically. We're doing this mentally so that we don't have to redraw this. We cut these bonds in half. And an electron from a bond goes to the left and one goes to the right. So it's like an electron sitting here. You take the number of valence electrons that that atom normally has. So for oxygen, it's 6. And you look at how many it's showing now. Remember, that bond split in half. There's an electron sitting here. So 1, 2, 3, 4, 5, 6, 7. 6 minus 7?
Negative.
Now 1. This oxygen has a negative charge on it. I want you to show that. The reason I'm doing that is some professors in college are going to require you to show it. You go to this nitrogen. Nitrogen normally has 5. Split all the bonds in half. 1, 2, 3, 4, 5. 5 minus 5 is 0. And then over here on this oxygen, normally has 6. 6 minus 1, 2, 3, 4, 5, 6 to 0. So those two are neutral, leaves me with a negative charge there, which is what I should be left with, a negative charge overall. Is anybody got any questions of where I'm getting that?
You're not done.
Nope.
Why am I not there?
Because
Because,
it has to be symmetrical.
yes.
You can't make it symmetrical.
So you draw the resonance structure.
Yeah, that one.
So I have to, resonance. The resonance is important.
Yes.
Now, today's a special day
No, sir.
because we're going to show you why resonance is so important. So on this, you're literally looking at a mirror reflection of it.
I hope you're recording. Oh, yeah, kill.
Alright. Now in this, remember, when you're doing resonance structures, you have to show a structure for everywhere that bond, that double bond or triple bond could have went. Okay? So if there's more places for it to go, then you're going to have to show it. So this right here is the actual answer. You must show the charges, and you must show the resonance. I will openly look at you and tell you, whenever you do take the quiz on this, this is how I phrase it. Give me the properly drawn Lewis structure of, and I'll give you some molecule. Within that, that's literally it. I tell you in the directions, show resonance if needed. Now in this, if you're like me, when I was at this level, I was always wondering why resonance mattered, because that literally looks identical to me. Nothing looks different, it's just a mere reflection. I could literally take this molecule and flip it and it's the same thing. How is it different? And it actually is different. What you do not see at this level is that molecules are not two-dimensional. That's why we don't like, I really don't enjoy doing Lewis structures a lot. They're actually three-dimensional. And within them, how they're shaped and what comes out and what goes back, literally where things line up, determine how things react. Like inside your body is a perfect example. How many of you have ever heard of a drug called thalidomide?
Can do one now.
Thalidomide. Thalidomide was the brainchild. I mean, it's the drug that literally was going to earn more money for a company than Viagra is today. Viagra was an accident, by the way, if you did not know
Wasn't
that.
it like heart medicine?
Yeah.
Yeah, they actually developed it to be heart medicine. I learned about it in my biochem class, is how the trials actually went, is they develop it for patients that have had heart attacks. So they get to the phase of the testing where they actually start testing on humans. They start giving it to humans, and they had more people die from a heart attack that took Viagra than people that didn't. And then they start sitting down and they start asking what the side effects and everything was from it. And they were like, oh boy, we hit the jackpot. So, thalidomide is one that was going to take the cake though. And this is as to why. Thalidomide was extremely useful for women that were pregnant for morning sickness. And this baby worked miracles. They could take thalidomide and no morning sickness whatsoever. It worked beautiful.
What about the bed?
Until it did.
But there were some issues. And within these issues,
Everybody don't take drugs, we have a body.
within these issues, it does not pop
Please
up.
don't sound like a helpless baby.
Did it give
Like,
it guys about your brain to
It'll
say
get
to take off the phone?
watch it come out.
Yes.
Right.
Here is your 411.
Yeah, I love TikTok.
My what now?
In the fall of 1960, Frances Oldham Kelsey was one of the Food and Drug Administration's newest recruits. Before the year was out, she would begin a fight that would save thousands of lives, though no one knew it at the time. Although she was new to the FDA, Kelsey was no novice as a scientist. After graduating from high school at age 15, she enrolled at McGill University in Montreal and earned both undergraduate and master's degrees in pharmacology. From there, she applied for a research post at the University of Chicago's Pharmacology Department. Her acceptance letter was addressed to Mr. Oldham. Kelsey later joked that had her name been Elizabeth or Mary Jane, her career might have ended there. Fortunately, it didn't. She earned her doctorate in pharmacology and accepted Chicago's invitation to stay as faculty, where she undertook pioneering research on drugs and fetal safety. In 1950, she earned an MD, her fourth and final degree. By the time she joined the FDA, Frances Kelsey was one of the most educated, experienced scientists around. Yet, as the newest member of the team, Kelsey was assigned what everyone thought would be an easy review, an application from the U.S. drug company Merrill to sell a drug called thalidomide. Thalidomide was a sedative developed in Germany that was already being widely used in dozens of countries to treat insomnia and workplace stress. Thalidomide's anti-nausea properties also made it a popular remedy for pregnant women with morning sickness. Reviewing Merrill's application, Kelsey found its data on thalidomide's absorption and toxicity inadequate. Today, the FDA classifies drugs based on their safety for a fetus. But in 1960, Many experts believe that the placental barrier shielded a fetus from harm. Kelsey's earlier animal-based research demonstrated the opposite. Drugs could pass from mother to fetus through the placenta. Like other drug companies at this time, Merrill had not tested its drug on pregnant animals. Kelsey later said Merrill's evidence for thalidomide's safety seemed more like testimonials than the results of well-designed studies. Kelsey rejected Merrill's application and asked them to submit a second, backed by better evidence. Her FDA colleagues supported this decision. Merrill had expected a quick affirmative reply so it could launch thalidomide for the holiday season, when sedative sales soared. Instead of supplying Kelsey with the data she requested, they first tried to convince her to approve the drug over a series of calls and visits. When these failed to sway her, Merrill executives complained that stubborn and nitpicking Kelsey was the problem, not thalidomide. The FDA backed Kelsey, forcing Merrill to file another application, and another, and another. As Kelsey reviewed and rejected each new application, news of thalidomide's adverse side effects began to surface. Doctors reported cases of nerve damage in early 1961, and by fall, they'd unmasked a more horrible truth. Thalidomide, widely used by pregnant women, caused severe birth defects. Thousands of babies died in utero, and tens of thousands more were born with extra appendages, shorter limbs, or no limbs at all. In November 1961, thalidomide was pulled from the German market. Nonetheless, Merrill continued trying to get it approved in the U.S. for several months before withdrawing their sixth and final application. While Kelsey wasn't the only scientist to identify the risks of thalidomide, she sounded the alarm that kept it off the multi-billion-dollar American drug market. As public awareness of the thalidomide tragedy grew, the quiet scientist became a media sensation. Headlines in newspapers and magazines heralded her heroism, while a smiling President John F. Kennedy presented her an award on the White House lawn. After the thalidomide scare, Congress passed laws that expanded the FDA's authority and toughened requirements for new drug applications. Kelsey was tapped to head the agency's drug investigation branch. Working at the FDA in different capacities into her 90s, Kelsey was able to witness the changes her actions helped inspire. Her visibility may have dimmed since, but her legacy endures. Privileging facts over opinions, and patience over shortcuts, she made evidence-based medicine the foundation of reforms that continue to...
She was 100. She was 101.
She was depriving a man of the ability to support his wife and child. Today, women make up almost 40% of the world's paid workforce, but they are still disproportionately unrepresented in STEM fields. Why? These students in our TED Ed Clubs program are asking the same question, and many are using the platform to share their scientific ideas, discoveries, and hopes with the world. Make space for your passion and join the movement to promote student ideas. Visit ed.ted.com/clubs to learn more.
That's what I want. I want to do that. I want to do TED.
Narration by Pen Chin.
The interesting thing is I stopped mirroring my phone and it's still playing the video.
Mine did that.
It's doing it again.
So what does I do in order for it to count?
Hold on, Tay. All right.
There's another one
So this is what you get, and you guys really won't learn what this really means until you take organic chemistry. So just leave it at the surface value of what I give you. Okay? We're going to use these two as examples. So within this, we would label one of these, what we would call it is the R enantiomer and the S enantiomer. So let's just say, for example, that this one here is the R. And this one over here is the S. And all this is saying is it's literally us labeling how it looks.
Resonance structure.
Yeah. So these enantiomers, they are shaped differently. And within the different shapes, they have different effects within what the process it's doing. So within this, they did more research on thalidomide, and they had found out that what was causing the birth defects was the S enantiomer. So in that, you would think that you could just take the S out, make sure that the pill is just R, and you're fine. There's no more issues. But the issue came about is that the R enantiomer within the body would literally change shape and turn into the S for no reason. It would just do it. And it literally was just based off of how the thing is shaped. The R enantiomer cured women's morning sickness like nobody's business. It was a godsend. But the problem of it is the R enantiomer would turn to the S, go through the placenta into the fetus, and once it got to the fetus, it was jacking everything up within the cellular development, and it caused all sorts of birth defects like you've seen there on the video. So, does resonance matter? Yes, resonance matter. And without it, you're going to jack something up bad. What?
How else did they think the fetus got its nourishment?
They did at that time. They didn't think that the medicine would go through the placenta.
So they know the food went through.
Yeah, so
it
what
provided
would
the
differ?
baby the
But what you guys have to understand is you're not looking and saying, I eat this Big Mac from Mickey D's and half of my Big Mac went through the placenta. Okay? It went through the digestive system. It broke the Big Mac down into the nutrients. It broke it down into those macromolecules. And that went through the
So
placenta.
has not the baby provided itself with that nourishment?
No. It breaks the food down. They're looking and saying that it would allow macromolecules through, like lipids, sugars, stuff like that. It would go through the placenta, but the medicine, there would be a barrier there that would look and say, this can't come through. It's the same thing like your blood-brain barrier. Your brain will feed off one sugar,
So they thought that the
Glucose.
placenta was
and that's it.
alive.
It won't feed off any other sugar. You can eat fructose all day. Your body will use it, but your brain won't. It'll only use glucose because the blood-brain barrier, that's the only sugar that can get across it. They're looking and thinking the same thing was taking place with the placenta, is that medicine couldn't get through. What?
So basically what they were thinking was the placenta only provided nourishment to the baby and it would leave out anything that was bad.
No, they were just looking and saying that the medicine would not get through.
Exactly. It was not.
But you're looking and saying the only thing that was getting through is macromolecules. That's not what they're saying.
Is it true that
Other things can get through.
you have type 2?
So they won't let the medicine through. They were thinking that the placenta wouldn't let the medicine through.
Yes. No, it's not.
What did you think I was saying?
You said that it would only allow the macromolecules through.
Huh?
You can't make that bold of a statement.
What do you mean?
You're saying only the macromolecules can get through. That's not saying the same thing I'm saying when I'm saying that other things are getting through except for the medicine. In my statement, in my scientific statement, what I'm stating is the medicine can't make it through. In your scientific statement, you're stating only macromolecules that are going to give this baby
Good stuff.
energy and nourishment
My
can get through.
statement, what I'm asking is, did they think that only those things could get through, or did they think that it would just keep the pills out?
They think that it would keep the pills out.
Okay.
All right. On for the fun stuff. Give this a shot. Give me a Lewis structure for phosphate.
Phosphate, bro.
What?
Like, it's been pregnant,
Mm.
get a tattoo.
I have no idea.
I know it basically like your subcutaneous like layers, which makes the tattoo stay forever. Does the ink get in the bloodstream?
Do what?
Does the ink get in the bloodstream?
I don't know. Never researched it.
So you would.
Right. Mr.
I'm
Hall,
gonna say that there's a chance.
He would be, let's say you had 17
the 3 negative after the thing is the charge.
Yep.
Okay.
So like it'd be like, so missing.
I can't remember my ISIS yesterday at all, it doesn't matter.
You did ask, and it does matter. The charge has to be in the back, because whenever we do oxidation and reduction states, we put charges in front. Like if somebody told me -3, then automatically I'm looking and that's an oxidation and reduction state. That's not a charge. There's a subtle difference.
But, okay, so like whenever you're looking at it, and then like as far as maybe the add and take one, is that still something that we're taking? Or, okay, is that something we take?
Mr. Hall?
Free?
Yes.
I know where you're gonna get people on this.
I've saved it.
Yep.
I've saved this one just for this moment.
Ha ha. Ha 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 ha. It's so funny. They come on. No, wait, no, don't. Don't look at, don't look, but look.
You're getting 32 electrons.
So confident that she has it. As I walk, she says, "No, no, 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 no." I can't remember what movie it was. I was watching a movie with my wife the other night, and I said, like, there was this guy that just stared at somebody. And I said, that right there is how I think my students feel when I look at them. And she said, yes, and I hate it when you look at me like that. What's the question?
When we get 29, do we add 3 to it?
Mm-hmm.
Okay.
Yeah, but.
Yeah, I don't know
You
what to
know,
do.
you're not doing
Wouldn't you add them little plus signs?
Michelle's trying to get out of the desk.
And a line through that one line?
Do you think that's something?
If there's a resonance structure, you have to show it. I don't know where you're at, so I don't know how to answer whether you need that or not.
Whack.
Carter,
What?
I've got more than I need. So I'm gonna have to ask. Because on these we put.
If there was a positive charge, would it show positive charge?
So I should still have.
What were you at before
You can.
But
As long as the overall charge matches the overall charge, that's what
Is
gives
it
it.
this?
I got it. Because it canceled.
Are gonna show it's like what negative?
Okay, so on this, you should find out you gotta have 32 electrons. Here should be your base structure for it. So let's count up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Woo! How nice. And then in this, at this point, hopefully you all are rolling through and you're looking and saying, this oxygen has a negative. Well, let's do it this way. Let's do it a different color. you're saying this oxygen has negative, this oxygen's negatively charged, that oxygen's negatively charged, and that oxygen's negatively charged. And then you look at phosphorus and you're like, well, snap, crackle, pop, that's got a positive charge.
Dun, dun, dun.
And many of you want to stop right there.
No, sir.
And for every one of you who want to stop right there, you are wrong. Can I get rid of charges?
Yes, sir.
Yeah.
How?
Because phosphorus will take 10 valence electrons. It'll form 5 bonds.
Phosphorus is an octet rule breaker. Phosphorus, if bonded with high electronegative elements, such as oxygen, chlorine, or fluorine, will break the octet rule and will form 5 bonds and take on 10 valence electrons. So in this, I can add in a double bond right here. Whenever I add that double bond, I can't break the octet rule here on oxygen. So that has to go away. A lone pair must disappear. On phosphorus, however, I can break it. So I can stay at the 10. And then you check everything out again. This oxygen normally has 6, and the charge of it's showing 6 now, so it's neutral. This phosphorus normally has 5, and it's showing 5 now, so it also is neutral. So I just got rid of 2 charges. But you have to check and make sure the charges stay the same as the overall charge. So in this case, this oxygen normally has 6, and it's showing 7, which gives me a -1, and these 3 oxygens are the same, so they keep the negative charges.
I'm not disappointed about that. You know what I'm disappointed about? You have to show the resonance structure and then do it with all 4 of them.
Yeah, you have to do all
That's
4.
on us.
We got to do all 4 and rotate it around.
Yay. Yeah.
What would you do if the charge, like, on the element was positive? Like, would you change anything or just subtract it?
What do you mean it was positive? So like it was here on phosphorus?
Like, no, like on the main top, the PO.
Oh, up here?
Yeah.
Then what you would do is you would subtract the electrons that we did here whenever we add them.
And that's all you do that's different.
Yeah. So I need a double bond there.
Mr. Hall?
Yep.
I love doing the same exact thing about 4 different times.
I don't. I hate these.
I was being sorry. So weird.
Ain't put it to the right yet, have
Okay, so how do we
That's me, right?
draw these?
I? Yes.
Mr. Hall,
Yep.
on your presentations, is this gonna be these islands or that big?
On Wednesday it's just Paulie Thomas. On Friday, everything. If you have questions, come ask me. Monday, you have a practice sheet. And there is phosphate.